Here I'm looking at question number 5. The picture here is bad. You should see that we have all positives here. And if they're all positive, then we would have forces of repulsion, which would force these away from each other. And this is not any way you could have a piece of magnesium metal, a solid piece of magnesium metal, which you saw in your lab. So we need a way of gluing these together. So here's a different picture. It still has these positive ions, so we can imagine these were the Mg+2 ions seen in the previous picture. But now there are these electrons. And you can imagine that with electrons, we'll have forces of attraction. These positives will be pulled toward the negative, and that will bond them all together. So instead of flying apart, then we can have attractive forces that bond. The word here is delocalized. So these are electrons that come from the magnesium atoms, but they are not fixed in place. They are mobile. That is the key to metallic bonding. We need mobile electrons. Here you can see an animation suggesting electrons moving between the stationary metal ions. We have electrons that are mobile. This is a model for metallic bonding. Here's a three-dimensional representation of metallic bonding. The blue spheres would be the metallic nuclei, which remain stationary. Around and between these nuclei are mobile electrons, which attract the positive nuclei to each other. We call this metallic bonding because all the elements that are metals look like this. I'll click on magnesium, for example, and you see here are these mobile electrons, sometimes called a sea, an ocean of delocalized electrons. Lithium is also a metal. You see a very similar picture. Aluminum. These all have a similar type of bonding. They're all metals. But if we look at something that's not a metal, like silicon, you can see here it's a very different type of bonding. This is very rigid. There are no mobile electrons. Similarly, carbon has varying structures, but they are all these rigid bonds, no mobile electrons.